Okay, in this lesson we're going to go over central angles and inscribed angles and how to find the measures of arcs and angles given certain measurements. So first we're going to talk about central angles. So remember, a central angle is an angle whose vertex is on the center of the circle. So this would be a central angle here. So central angle, the measure of the central angle is equal to the measure of its intercepted arc. So remember, the intercepted arc is the arc between the endpoints of your angle. So AC are my endpoint, so the intercepted arc would be AC. Okay, so the measure of the central angle, which would be that, is equal to the measure of the intercepted arc. Okay, so if we were to put that in symbols, we would say the measure of the central angle, so the measure of angle AOC is equal to the measure of arc AC. Okay, so the central angle is AOC and the intercepted arc is AC. Okay, so for instance, if the measure of angle AOC was 25 degrees, then that means the measure of arc AC would also be 25 degrees. So the way that I remember this is I say that the central angle is the same, since they both have an S sound. Central, same. Okay, the arc addition postulate states that the measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. So to see what I mean visually, it's basically just saying that the measure of arc AB, which is this arc right here, plus the measure of arc BE, which is this arc right here, that's going to be equal to the whole entire arc. So the measure of arc ABE. And ABE, oops. ABE basically goes from here all the way to here. Okay, so it's essentially saying that this part plus this part equals this whole entire part. Okay, which should seem logical to you. So for instance, if I told you that the measure of arc AB was 75 degrees, and I told you that the measure of arc EB was 25 degrees, that means the measure of arc ABE would just be 75 plus 25, which is 100 degrees. So the measure of arc ABE is 100 degrees. Okay, so now let's look at a couple examples and how we can use both the central angle and arc addition postulates to solve for missing arcs and angles. So when you're doing these types of problems, when you're given, say, a circle and you have a bunch of central angles like here, it's going to look like there's not enough information. So what you want to look for is you want to look for semicircles. So remember, semicircles are formed by a diameter, basically cuts a circle in half. The reason we look for semicircles is because semicircles are 180 degrees. And that allows us to have more measurements than what's just given to us in the picture. So in looking at this diagram here, we want to name all the semicircles we see. So to look for semicircles, look for diameter. So the first diameter C is AD, which forms two semicircles. It forms the semicircle on top and the semicircle on the bottom. So the semicircle on top, I'm just going to call ABD. So ABD is one. And then we have the semicircle on the bottom, which is AFD. And then another diameter I see is BE, because that goes to the center of the circle. So BE is a diameter, which means one semicircle might be BCE. And then we have the semicircle on the other side. So BCE is up here. That means BAE is a semicircle on the bottom. So again, the reason why we're identifying semicircles is because we know that there's 180 degrees in a semicircle, which is going to allow us to solve for missing parts. So for these types of problems, what I want you to do is I want you to solve for all the missing pieces first. Okay, and then you can answer the question. So in looking at this diagram here, the pieces that I don't have a measurement for are this one, and this one. So a couple other things you're going to want to look for. You're going to want to look for vertical angles. Well, if we know that this angle right here is 18 degrees, then that means this angle right here is also 18 degrees. And remember, for now, we're not differentiating between arcs and angles because we know that central angles and arcs are the same. Okay, we know that this angle right here is 90 degrees because that's what the box means. So now the two pieces that we need this piece right here and we need this piece right here. So this is where the semicircles are going to become helpful. So in looking at this bottom part right here, we have the semicircle AED. Okay, AED is a semicircle. And we know that there's 180 degrees in a semicircle, which means that, sorry, I just realized that my semicircle here is wrong. This should be AED, not AFD. So AED is a semicircle. There's 180 degrees, which means that if I wanted to solve for this missing piece, I could just do 180 minus 18, which is 162 degrees. So I have that piece, and the last piece I need is this piece up here, okay? And this piece right here is a part of a semicircle. So if we look at this semicircle right here, it's formed by three pieces, the 90, the 18, and this unknown piece. Since it's a semicircle, we know that's 180 degrees, so to find this piece, we can do something similar that we did in triangle sum theorem. I could do 18 plus 90, which is 108, and then I can subtract from 180 since there's 180 degrees in a semicircle, which is 72 degrees. So this piece right here is 72 degrees. Okay, so now that I have all the missing pieces, now I can answer these questions. So now we're asking for arc CE. So CE is this part right here. So we have these central angles, 90 and 18, and we know that the arcs are the same. So CD is going to be 19 and DE is going to be 18. And then using the arc addition postulate, we can just add those together, 90 plus 18, which is 108 degrees. So the measure of arc CE is 108 degrees. Okay, now we want to solve for AFE, so that's a central angle, so AFE. So we've actually already solved for that. It's just going to be 180 minus 18, which is 162 degrees. So the measure of angle AFE is 162 degrees. Okay, let's look at another example here. So using this diagram, again, it's helpful to identify the semicircles. So you only need to do this if it asks you to, but I do think it's helpful. So look for diameters when looking for semicircles. So here's the first diameter. So one semicircle I see is KLN. Okay, and then we can do the other side. So KJN. And then another semicircle I see, I have this diameter right here, JM. That means I have JKM. And then I have the reverse side. So JKM, the other one would be JNM. So remember, semicircles means 180 degrees, and that's going to help you solve for the missing parts. So the next thing I'm going to look for before I answer questions 2 through 4 is I'm just going to look for vertical angles. So I have two lines that cross here. This one's 25 degrees. That means directly across is also going to be 25 degrees because they're vertical. And now let's solve for the missing parts. So the first piece I'm going to solve for is this piece right here. And when looking at this, I see that piece as being a part of the top semicircle here. Okay, so KLN is a semicircle. So I could add these two together and subtract from 180. It's going to give me this angle right here. So 40 plus 25 is 65 degrees. And then we're going to subtract from 180. So 180 minus 65 is 115. So this angle right here is 115 degrees. Okay, I can do a similar thing for this angle right here. Okay, so I see that piece as being a part of this semicircle, and this semicircle is made up of two pieces. It's made up of this 25, and it's made up of this big piece right here. So to solve for that piece, I could just do 180 minus 25, which is 155 degrees. So this angle is 155 degrees. Okay, so now that I have every piece of my pizza or pie, okay, now I can answer these questions. So first one, they're asking for arc JL. So JL goes from here to here, okay? And remember, central angle is the same as the arc. So since I have these central angles, I know the arcs are just going to be the same. So if I'm solving for JL, it's just going to be these two pieces added together. So it's just going to be 25 plus 115, which is 140 degrees. So the measure of arc JL is 140 degrees. Okay, now we're going to look for angle KPL. So KPL is this angle right here. And we actually already did the math for this one. So KPL, there's the math for it. Okay, KPL was just that piece which is part of the semicircle, so we just did 40 plus 25 and subtracted that from 180. So the measure of angle KPL is 115. Okay, the last piece we're solving for is LJN. So LJN goes from here all the way to here. So that's made up of, I guess there's a couple ways you can think about it. You can think of it as it's made up of these three pieces, or you can use the fact there's 360 degrees in a circle, and it's everything but these two pieces. So to me, that's a little bit math that I need, less math than we need to do. We know that 40 plus 25, this piece right here is 65 degrees. So to find LJN, which is everything but this piece, we can just do 360, which is a full circle, minus 65, which is 295 degrees. Okay, you would get the same answer if you just did 115 plus 25 plus 155. But to me, this is a little bit easier. So the measure of arc LJN, which is a major arc, because it's over 180 degrees, is 295 degrees. All right, now I'm going to go over inscribed angle theorem. So inscribed angle theorem states that the measure of an inscribed angle is half the measure of the intercepted arc. Okay, the other way you can think about it is the intercepted arc is twice the measure of the inscribed angle. Okay, so in looking at this picture, my inscribed angle is angle, and I'm missing a letter here, we're going to call that letter C. Angle ACB is my inscribed angle. Remember, what makes an inscribed angle inscribed is that the vertex is on the circle. And then arc AB is my intercepted arc. The intercepted arc is just the arc between the endpoints of the angle. Okay, so if I said that the measure, so I guess putting this into symbols, we can say that the measure of the angle ACB is equal to the measure of the arc divided by 2. Okay, or you can think of it this way. You can think of it as the intercepted arc is 2 times the measure of the inscribed angle. Okay, so putting in to numbers here, if I knew that my angle was 15 degrees, my arc is just twice that, which means my arc would be 30 degrees. And you can also reverse it. If my arc is 30, my angle is 15. Okay, the other way you can write this just without any symbols is you can just say that the inscribed angle is just the arc divided by 2. Okay, or you can think of it as the arc is 2 times the inscribed angle. Okay, so let's look at a couple examples here. Okay, so in looking at this picture, let's look at the inscribed angle. So the first inscribed angle I see is SRU. Okay, so that's an inscribed angle. And the intercepted arc, remember, is just the arc between the endpoints. So the arc would be SU. Okay, another inscribed angle I see is RST. So RST. And the arc for that angle is just going to be RT. Okay, so first thing we're doing is we're finding the measure of SU. So SU is this arc right here. And the angle for that arc, so if this is our arc, the angle for that arc is going to be SRU. Okay, so remember the arc is just 2 times the angle. So if we multiply the angle times 2, we're going to get the arc. So 2 times 40 is 80. So the measure of SU is 80 degrees. Okay, now we're looking for the measure of RST. So RST is the inscribed angle. And we have the arc for that inscribed angle. So the intercepted arc is 120. So to get to the angle, it gets smaller. We divide by 2. So to find RST, we take the arc, which is 120, and divide it by 2, which is 60 degrees. So the measure of angle RST is 60 degrees. All right, let's look at a couple more examples that are a little bit harder. Okay, so they want us to solve for x, which is in this angle right here. So if we look, you should see 2 different inscribed angles. So the first inscribed angle is EDF, and the second inscribed angle is EGF. If you notice, those 2 inscribed angles have the same intercepted arc. So angle EDF and angle EGF have the same intercepted arc. Okay, since they have the same intercepted arc, that means the measure of angle EDF has to equal the measure of angle EGF. Right, so if 2 angles have the same intercepted arc, that means the angles have to be equal. And if these 2 angles are equal, that means 2x plus 3 equals 27. Okay, from here it just becomes a simple algebra problem. We subtract 3, so 2x equals 24, and then divide by 2. So x equals 12. Okay, what you could do is you can always take this and plug it in here. So 2 times 12 plus 3, and it should equal the same thing here, which it does. It equals 27 degrees. All right, number 5, we're solving for z. Okay, so z is right here, and it might look like this doesn't have enough information. However, you should notice that CA is a diameter. And when CA is a diameter, it cuts the circle in half. So CA is a diameter. So it cuts a circle in half. And remember, if it's cut in half, that means there's 180 degrees on both sides. So that's telling me that this arc right here is 180 degrees. Well, if that arc is 180 degrees, that tells me that the inscribed angle is just going to be divided by 2. So to get the angle from the arc, we divide by 2. So that means this angle right here is 90 degrees. So if that angle is 90 degrees, that means we can say 8z minus 6 is 90 degrees. And now we can solve for z. We add 6. And then we can divide by 8. So that means z equals 12. Okay, to check our work, we can always take it and plug it back in here. So 8 times 12 minus 6. 8 times 12 is 96, and 96 minus 6 is 90 degrees. So that's just the work to check it.